Good morning, everybody. Today we will continue with momentum, impulse, and collisions. What we have this in the content of this lecture, we will talk about the momentum of a particle, and then we will see the relation between the net force acting on the particle and also the momentum. Okay, so in addition to that, we will learn what is the impulse and what is the relation between the net force and impulse. What is the relation between impulse and the change in the momentum? We will learn all these things within this chapter. In addition to that, we will talk about the conservation of momentum, very important, sometimes dealing with some problems. And we will continue with elastic collisions, inelastic collisions, and also completely inelastic collisions. Then with the center of mass and also rocket propulsion, we will finish this chapter. So probably I will finish this part of my lecture, elastic, inelastic, and completely inelastic collisions within this lecture. And on Thursday, I plan to continue with the center of mass and also rocket propulsion. So why we need this momentum and impulse? Why the other chapters related to the Newton's laws of motion are not enough? Because sometimes problems can be very complicated. Look at this picture here. There is a carrot, and there's a bullet here. You can see a bullet hits a carrot, okay? And here we have very complicated forces. So by using Newton's law, it is not so easy to solve such problems, okay? Then you have to use momentum, impulse, and conservation of momentum to solve such problems. So it is very useful if the Newton's law cannot help you to solve very complicated problems where you don't know the complicated information about the forces. Let me introduce the momentum first of all. So remember the Newton's second law, which is given with net force acting on the object is equal to m times a, right? So instead of a, I can write time derivative of velocity because acceleration is given with this definition, okay? So just take this mass here into the derivation, and then here we have this type of relation, time derivative of m times v. So this m times v is called as momentum or linear momentum of the particle, okay? Momentum of particle is given with m times v. The important thing here is that momentum is a vector, okay? Here we have velocity, which is also a vector, and the direction of the momentum is the same as the direction of the velocity. Here we have a particle with some certain mass in the graph, and it has certain velocity in some certain direction. Then we have momentum, which is given with this magnitude and this direction, okay? Momentum P is a vector quantity, don't forget this one. Okay, you can also write the momentum in terms of its components. So this is the x momentum, momentum along the x-axis, which is given m times vx, and this is y momentum, this is z momentum, okay? So what about the unit of the momentum? Look at the mass here, the unit is kilogram, right? And here we have velocity, unit is meter per second. So the SI unit of the momentum is kilogram times meter per second. And here we have one momentum, one momentum, one momentum. And here we have three momenta, okay? The plural of momentum is momenta. Now let me continue with this definition. Look at this one here. Net force acting on the object is given with the time derivative of this m times v, okay, velocity. So I can write this expression like this. Net force acting on the object can be written with the rate of change of the particle's momentum, dp over dt. Okay, then let me define the impulse and the relation between impulse and momentum. Remember the work energy theorem in the previous chapter. So within this chapter, we have impulse and momentum theorem. So the mechanism is more or less same. You can easily keep in your mind. So I will go into detail. What is the impulse of the net force? Here we have impulse. We denote the impulse with capital J, okay? Of course, it is also a vector, don't forget. And the impulse of the net force is defined to be the product of the net force and the time interval. So you apply net force on the object for certain time interval, delta t, or t2 minus t1. So this is the impulse of a net force. And let's try to find a relation between impulse and momentum. Look at this expression. What we have here, the net force is given with the rate of change of the particle's momentum, right? So if net force is constant, let's consider that here the net force is constant, then in this equation, let me write it here, net force is equal to dp over dt, okay? So if the net force is constant here, this one is constant, then this is also constant, okay? Then I can write this expression like this. Delta P over delta T, okay? If the net force acting on a system is constant. So delta P can be written with this expression, final momentum minus initial momentum, and delta T can be written in this form, final time minus initial time. Then what we have here, we have net force acting on the object. Here we have delta T. If you multiply them, then on the right side, we have this expression. Look at this one. What is this? Look at this one. This term on the left side is equal to J, impulse. And look at this one on the right side. This term is equal to delta P, okay? Then we can write an expression between J and delta P, between impulse and change in the momentum. Then this is the impulse momentum theorem. The impulse of the net force on a particle during a time interval equals the change in the momentum of that particle during that interval. So here we have impulse of net force over a time interval, and this is the change in momentum. Remember the formula during the last lecture, work energy theorem. Work done on a particle is equal to delta K. K final minus K initial, okay? It is like this. The impulse momentum theorem is very similar to the work energy theorem, okay? Here we have on the left side, we have impulse. On the right side, we have change in the momentum. So remember the SI unit of the work, it was joule, right? And what was the unit of the kinetic energy or change in the kinetic energy? It is also joule, okay? So What about the unit of the momentum? We have already given kilogram meter per second. So what about the unit of the impulse? It is same, kilogram meter per second. Okay, you can also get this expression from this formula. I mean, get the unit from this formula. So in this calculations, we have considered that the net force is constant. Okay, but just consider that the net force is not constant. So then what will happen? If the net force is not constant, let me write the equation. This is the net force. This is the time derivative of the momentum. Okay. And here we have non-constant net force. If you write this expression like this, and on the right side we have dp, and if you take the integral from time 1 to time 2, initial time, final time, and here on the right side what we have dp, okay, on the right side. Look at initial momentum of the particle, final momentum of the particle. And what about the solution of this integral? The solution of this integral is P2 minus P1. The integral on the left side will give us this impulse. Remember the impulse. This is the impulse of a general net force, and this is equal to delta P. What we see here that the impulse momentum theorem, this expression, impulse momentum theorem, is valid whether the net forces are constant or non-constant, like work energy theorem. Okay, it was also the same. Okay, remember this information from the previous chapter. So then impulse of a general net force, either constant net force or varying net force, impulse can be written with this expression, the integral from lower limit initial time to upper limit final time, and net force acting on the system, and the time integral of the net force. What will happen if the net force is constant? If the net force is constant, then you can take this constant value from the integral. Then here we have T1, T2, dt, and the solution of this integral is T2 minus T1. So the result is this one, T2 minus T1. So look at this expression, delta T. If the force is constant, then I can get this expression for the impulse of a net force. If the force here within this integral is not constant, then I have to use this integral to calculate the impulse of a general net force. Do you have any question until this point? So up to now, we have learned 4 equations: momentum and net force relation. We have learned net force and impulse relation. We have learned impulse momentum theorem. And we have learned impulse for varying forces. Okay, let's consider that net force is constant. We have discussed it here. Then the equation here will be like this. We have already discussed. But if the net force is not constant, then what will happen? sometimes we can use an average net force, okay? If the net force is not constant, I will also show this information on the graph, then you will better understand. So let's consider that we have an average force acting on the system. Force is not constant, it is changing by time, but in total we have some average force, okay? So I can write this non-constant forces as average force, like average velocity. Remember also average acceleration, okay? If the force is non-constant, I can write it like average force. Then here we have delta t. So for non-constant net force situations, impulse can be written like this. But if net force is constant, then this is constant, and this equation goes to this expression which we have found in the previous transparencies. Any question here? Okay, now let me show you these solutions, these results on these two graphs. Here we have time axis, and here we have net force axis. Here we have force, okay? And what do you see if you look at this red curve? The force is changing by time. At the beginning, when the time is t1, the net force is 0, and the force is increases by time. And here, when the time is certain number, we have maximum net force acting on a system, and then force is decreasing, and when the time is t2, net force is 0. So what we have here within the red curve, we have non-constant force, okay? Net force is not constant. So what about the area under this curve? The area under this curve can be written with this integral, okay? From t1 to t2, net force dt, okay? So what about this one? This is equal to the impulse, which we have discussed in the previous transparency. But instead of this expression, I can also write this area like this. Look at this green curve here, or green rectangle, let's say. So what we have here, we have average force, which is constant, okay? We have constant force. When the time is t1, we have force this one. When the time is some certain time, force is constant, okay? So I take an average force and look at the area under this red curve and look at the area under this green curve. So both areas are same, okay? So then I can write this expression like this. The area under this green curve is average force times delta t, right? So both of them are equal to the impulse along the x-axis. So here we have discussed this one, and here we have the solution or explanation on this graph. So now let me discuss this term on this equation, on this graph. Here we have again time, and here we have net force acting on a system along the x-axis, let's say. So here we have blue curve, and here we have yellow curve. So look at this blue curve. What we have here, at the beginning force is 0, and force increases very fast, okay? And we have very large force that acts for a short time, okay? Look at the delta t here. Delta t is very small compared to this yellow curve. So in a very short time, we apply large forces. And look at this yellow curve. In a very long time, delta t is here very long. But what about the magnitude of the net force? Magnitude of the net force is smaller than the blue curve. But what about the result? The area under this blue curve and the area under this yellow curve. The area is given in both cases with this expression. integral from T1 to T2 net force dt, okay? This is the area under this curve and area under this curve. So what about the result? If the area under these two curves is the same, then the both forces deliver the same impulse, okay? So this large force acts for a short time, and this smaller force acts for a longer time, but they deliver the same impulse J, okay? Any question here? So this dt is very important. The time interval is very important, and also the magnitude of the force is very important when you are discussing the impulse, magnitude of the impulse. Okay, then let me show you a bio application. The pileated woodpecker has been known to strike its beak against a tree up to 20 times a second and up to 12,000 times a day. The impact force can be as much as 1,200 times the weight of the bird's head. Because the impact lasts such a short time, the impulse, the product of the net force during the impact multiplied by the duration of the impact, is relatively small. We are talking about the impulse produced by this woodpecker. Look at this J here, net force and delta T. Force is big, okay, compared to the weight of the bird's head, but what about delta T? Delta T is very short time, then the impulse will be relatively small, okay? If you look at this expression, you have big force compared to the weight of this bird, but since delta T is very short time, then the impulse is relatively small. In addition to that, the woodpecker has a thick skull of spongy bone, as well as shock absorbing cartilage at the base of the lower jaw, and so avoids injury. And let me discuss the car accidents and what is the relation between impulse and momentum in car accidents. Here we have, let's say, an occupant within the car, and there is an airbag, and here you see steering wheel, okay? And let's consider that the car is moving with some certain initial velocity, and this occupant has some certain momentum P1, okay? This is the initial momentum of the occupant here, or driver, you can say. This is the initial momentum. And when the automobile is stopped, then what about the movement of this guy? Due to the inertia, this occupant will move in this direction. And what about the final momentum of this driver? The final momentum will be zero, okay? Because velocity of the driver will be zero. So initial momentum is in this direction, some certain magnitude, and this is the final momentum of the driver. And what about the effect of the airbag? Okay, let's consider that there is no airbag, and in the second situation, consider that we have airbag. Now let me write the equation. Impulse is given with delta P, change in the momentum, and it is also given with F average delta T. The first condition, let's consider that there is no airbag. What about the change in the momentum? At the beginning, momentum is P1, and at the final condition, momentum is zero. So we have some certain delta P, right? And what about delta T? If there is no airbag, this guy will reach to the steering wheel here, in a very, very short time, okay? So this delta T will be very short. Then, since delta P is constant, then we will have huge force exerted by steering wheel on this occupant, on driver. Then there will be huge force, okay, if there is no airbag. Now let's consider that here we have an airbag. Write the equation again, impulse, the change in the delta P, F average, delta T. So what about delta P? Final momentum minus initial momentum. So here we have some certain delta P, and here we have same delta P, okay? Delta P does not change. So what about the effect of the airbag? The airbag increases this delta T time, okay? So it extends the time to reach this guy to the steering wheel, okay? So since here we have huge delta T compared to this shorter delta T, then we have lower force. Then the driver is not injured, okay? This is the relation between impulse and momentum, and the momentum and net force acting on the object in car accidents. Any question here? Is it clear for you? Okay, let me compare the momentum and kinetic energy. In the previous transparencies, I have written the work energy theorem, okay, and I have compared this impulse momentum theorem. So look at this one. Work is scalar, kinetic energy is scalar, impulse is vector, and momentum is also a vector, okay? So this is the work energy theorem, this is the impulse momentum theorem, and here we will compare the momentum and kinetic energy. So here there is a baseball pitcher, okay? And the kinetic energy, here there is a baseball, okay? The kinetic energy of a pitched baseball is equal to the work the pitcher does on it, okay? So the pitcher does a work on the baseball, and the kinetic energy of the baseball changes, okay? At the beginning, kinetic energy is 0, and in final condition, we have some certain kinetic energy. Okay, this is due to the work done by the pitcher on the baseball. And what about the work applied by work done by the pitcher, which is given with net force times displacement, right? This is the work done by the pitcher. Pitcher applies a force, and the force is applied with some certain displacement. So this is equal to the change in the kinetic energy of the ball. And what about the impulse? So the delta P is written with this expression, final momentum minus initial momentum, and it is given with this expression. Look at the impulse. The impulse can be written with this expression, net force acting on a system and delta T, okay? So within this same example, you can use either this expression or this expression, okay? Work energy theorem gives us the change in the kinetic energy and work relation, and work is written with this expression. displacement times net force acting on the baseball, and the impulse momentum theorem gives us the change in the momentum, and it is given with net force times delta t. Okay, this is the comparison of momentum and kinetic energy. Any question here? Okay, then let me continue with the example. Example 8.2 from the book. A ball hits a wall. You throw a ball with a mass of 0.4 kilogram against a brick wall. It is moving horizontally to the left at 30 meters per second. When it hits the wall, it rebounds horizontally to the right at 20 meters per second. Find the impulse of the net force on the ball during its collision with the wall. J is asked. Okay. If the ball is in contact with the ball for 0.01 second, find the average horizontal force that the wall exerts on the ball during the impact. So F average is asked. Okay. So now let's try to calculate the momentum. This is the initial momentum of the particle, P1x along the x-axis. This is before the collision, which is given m times v1x. M is given, and instead of vx, I am using minus 30 meters per second. If this is plus x direction, positive x direction, this is negative x direction. So here I have to put minus sign. Then I have negative sign of the momentum. Momentum is a vector, okay? This negative sign is showing that the direction of the momentum is along the negative x at the beginning, before the collision. Then the final momentum of the ball, m times v2x, and it is given with plus 20 meters per second. And this is the momentum of the particle, momentum of the ball, let's say. And what about the impulse of the net force on the ball during its collision? So we don't know the force. Actually, impulse is given with this expression, right? Net force times delta t. But we don't know the force, okay? So how to find this impulse? Impulse is also given with delta p, right? This is the impulse momentum theorem. Then apply this theorem here. Impulse is given with change in the momentum, delta p. Then you know the final momentum, p2, just put it there, minus initial momentum. Initial momentum is given with negative sign, and here we have another negative sign. Then the result will be positive. This is the change in the momentum. 20 kilogram times meter per second. We can also write this expression with this unit, Newton times second. So what was the second question? Find the average horizontal force that the wall exerts on the ball during the impact. So this is asked. How to find this one? We have written the expression here. I know the impulse, I have calculated. I know the delta t, which is given in the question. Then I can calculate net force. Net average force is given with impulse over delta t. Impulse is calculated. Delta t is given in the question. Then I have average force applied by the wall on this baseball is given with 2000 Newton. Okay, and remember the direction of momentum in your calculations. If you don't use minus sign here, then you can get wrong results, Don't forget. Any question here? Another example from the book, kicking a soccer ball. A soccer ball has a mass of 0.4 kilogram. Initially, it is moving to the left at 20 meters per second, but then it is kicked. So this is the ball. It is moving to the left along the negative x direction with some certain velocity. And then here at that point, it is kicked, okay? So after the kick, it is moving at 45 degrees upward and to the right with the speed of 30 meters per second. This is the ball, soccer ball, after the kicking, and this is the velocity after the kicking. Okay, so what is the question? Find the impulse of the net force and the average net force. J is asked, and net force, average net force is asked, so delta T is given. So here we have force applied by this guy, but this force has some certain components along the x and y axis. Okay, and look at the ball here. This is the direction of the velocity, final velocity, and direction of the final momentum. So then momentum has also x and y components. Okay, then you have to apply components of momentum. Don't forget. Here we have 45 degrees. And if you use cosine 45 and sine 45, which are equal to 0.707, then you can calculate the components of the velocity and components of the momentum. So let's start with the velocity at the beginning, okay? When the ball is moving with some certain velocity to the left. So this is the initial velocity, v1x, which is equal to minus 20 meters per second. Why minus? Because it is along negative x. This is the velocity along the y-axis. The ball has no velocity component along the y-axis at the beginning, so it is 0. And what about the velocity along the x-axis after kicking, which is given with velocity times, so this component, velocity cosine 45, and this component, velocity sinus 45. So since cosine 45 and sinus 45 are equal to each other, then the x and y component of the velocity after kicking are equal to each other, 21.2 meters per second. Okay, so both of them are in positive direction. Okay, x component is along the positive x and y component is along the positive y. So both of them are positive here, don't forget. And then what about the impulse? Impulse is equal to change in the momentum along the x, okay? The change in the momentum along the x can be written with m times v2x minus v1x. We have calculated velocities, put them here, then this is the change in the momentum along the x-axis, kilogram times meter per second. And what about the impulse along the y-axis? This is equal to the change in the momentum along the y-axis. Then you can get this expression. Okay. So what about the net force? This was the second question. The average net force here. Average net force has also two components, x and y components. Okay. Then x component can be calculated with this expression, Jx over delta t. Why? Because we know that the impulse is given with average force average net force delta T. Okay, you will apply this relation. Then this is the X component of the net force. This is the Y component of the net force. And by using the X and Y components, you can calculate the magnitude of the force vector. You can also calculate the direction of the force vector applied by this guy. Any question here? Okay, now we will continue with conservation of momentum. If you are talking about conservation of momentum, you must consider an isolated system. So what we mean with the isolated system? In an isolated system, just consider here we have a body A and here we have a body B, okay? So let's consider that no external forces act on this body A and B. Let's consider this is a complete system of two bodies and there is no external force act on this system. So if there are no external forces, we have an isolated system, okay? Don't forget this one. So here, let's consider that this body A touches on this body B and applies some certain force, and this body B applies the same force with the opposite direction, okay, on this body A. But these forces, this guy applies on B and B applies on A, these are the not external forces. These are internal forces, okay? Because this is a complete system, an isolated system, and the forces within this system are the internal forces. So if there is no external force acting on this system here, then the total momentum is conserved, okay? In an isolated system, if there is no external force, then the total momentum of the system is conserved. Here we have two astronauts. They push each other and they are in space. There is no gravity, no other external forces, and the total momentum of these two astronauts is conserved. So now let me go into detail a little bit. Here we have astronaut A, and this is the force applied by astronaut B on astronaut A, force B on A. And here on this one, there is a force applied by astronaut A on astronaut B. So the forces the astronauts exert on each other form an action-reaction pair, and these are the internal forces, okay? They apply to each other. You can consider yourself, okay? So can you see my hand? So here I am using my hand and I am applying a force on my chest, okay? So I am applying a force on my chest and my chest applies a back force on my hand due to the Newton's third law, okay? Action-reaction pair. So then this force I applied on my chest and my chest applies a force on my hand. These are the internal forces, okay? If I am isolated, if there is no external forces, then the total momentum of the system is conserved. So now let me go into detail a little bit. Here we have defined force B applied by B on A, and on the right side, force A applied on B, okay? They can be written like this. We have learned that net force acting on the system can be written with the rates of change of momenta of the particles, okay? So here we have dp over dt for the particle A, the change in the momentum of A object. And here on the right side, we can write this Fa on B with the change of momentum of B, okay? So what about FB on A, what about FA on B? They are equal in magnitude, but they have opposite directions, okay? So I can write it like this. So if I take this one to the right, to the left side, then I can get this expression. FB on A plus FA on B are equal to 0, okay? Because they are same in the magnitude, but they are in opposite directions. For this reason, the sum of them is 0. So now, instead of this FB on A, just take this dP over dt, and instead of FA on B, just use this expression and use them here. Let me show. So just take this one here and just take this one here. Then finally you can get this expression. FB plus FA are equal to the rate of change of momentum of A object and the rate of change of momentum of B object, okay? So you can write this expression in this form. Here we have momentum of A object. Here on the right side, we have momentum of B object. And what is PA plus PB? PA plus PB, this is the total momentum of the isolated system, okay? So the rate of change of the total momentum of the system is 0. So here we have total momentum of the system, and the rate of change of total momentum, P, is 0. Then, what about this one? If the time derivative of momentum is 0, it means that P is constant. Okay, P does not change. Momentum is conserved. Okay. So, but here we have considered that this system is isolated. There are no external forces acting on this system, okay? We have only action-reaction forces, which are the internal forces, and there is no external force acting on the system. If there is no net force, net external force acting on the system, then momentum is conserved. Any question here? Then let me continue. Here we have skaters, okay? You can consider like this isolated system, which we have discussed in case of astronauts. Here we have skaters. And what kind of forces are acting on these skaters? So look at this A. This is the free body diagram of A. There is a weight downward and there is a normal force applied by the surface. This is upward, and there is force applied by B on A, okay, this one. What about friction force? We consider that the frictionless surface. So now just try to write the free body diagram of this lady, another skater, weight, normal force, and force applied by A on B, okay? So what about the normal force and weight? Normal force and weight here. They are equal to each other. So the net force, net external force, these are the external forces, normal force and weight. Here weight and normal force are the external forces, and the sum of the external forces is 0. Then the total momentum is conserved. Okay, net external force is 0. What about this force? What about this force? If you consider these two skaters as an isolated system, this force force B on A and force A on B are not the external forces. These are the internal forces, okay? If you consider this system is an isolated system. So external forces, the normal force and gravity here, act on the skaters shown, but their vector sum is 0. Therefore, the total momentum of the skaters is conserved if you consider that this is an isolated system. Okay, so now we have general definition of conservation of momentum. If the vector sum of the external forces on a system is 0, the total momentum of the system is constant. It does not change. Okay, so here we have discussed two body system, body A and body B. Here also we have discussed two body system, body A and body B. In some cases, there may be many particles, okay? Many number of particles, A, B, C, D, okay? So the total momentum of this system consists of many particles, can be written with momentum of the each particle, each object within this system, okay? So if there is no external force acting on this system, this total momentum of the system is constant. So these particles, these objects in this system can apply forces each other and their individual momenta can change, but the total momentum of the system is constant, okay? So this is the conservation of the momentum. Now, let me again remind you that the momentum is a vector, and when you are applying conservation of momentum, always consider that the momentum is a vector quantity, and you have to use vector addition, okay, to add different momenta. So here we have A object, it has certain PA momentum. Here we have B object, it has certain PB momentum. And this is the magnitude of the PA. This is the magnitude of the PB. Okay, so a system of two particles with momenta in different directions. So you would like to get the total momentum of the system. And if you write it like this, momentum of A particle plus momentum of B particle, then this is the wrong, because these are the vectors. You have to use vector addition, okay? Just use vector addition. This is the PA, this is the PB, and this is the vector sum of PA and PB. This is the correct total momentum of the system. Okay, don't forget this one. Now let me continue with the example. Do you have any question until that point? Example 8.4 from the book, Recoil of a Rifle. A marksman holds a rifle of mass 3 kilogram loosely so it can recoil freely. He fires a bullet of mass 5 gram horizontally with a velocity relative to the ground of 300 meters per second. What is the recoil velocity of the rifle? What are the final momentum and kinetic energy of the bullet and rifle? So, conservation of the x component of total momentum. Just write the initial momentum, total momentum of the system. At the beginning, both rifle and bullet have 0 momentum, okay, because they are at rest. So the total momentum of the system is 0. And what about the final momentum of the system? The rifle and the bullet are initially at rest. So the initial x component of the total momentum is 0. After the shot is fired, the bullet's x momentum is this one, and the rifle's x momentum is this one. Okay, so this is the initial momentum of the total system. It is 0. And after the shot, then this is the final momentum of the bullet. This is the final momentum of the rifle. Okay, so mass of the bullet is given, mass of the rifle is given. So velocity, final velocity of the bullet is also given here. Then I can calculate the final velocity of the rifle. It is given with minus 0.5 meter per second. Why minus? Because bullet is going in this positive x direction, but the rifle recoils in negative x direction. So what about the final momenta and kinetic energies? So we know the final velocity of the bullet, we know the mass of the bullet, then you can calculate the final momentum of the bullet. What about the kinetic energy? Kinetic energy given with this expression. Again, you put them here, then we have this expression. This is the kinetic energy of the bullet, 225 joule. And what about the momentum of the rifle? Put the mass of the rifle here, velocity of the rifle here. Here we have negative sign, don't forget. Momentum is a vector. Then here we have a negative sign. This is the momentum of the rifle to the left side along the negative x direction. What about the kinetic energy? Kinetic energy is given with this expression, 0.375 joule. So here we have an important information. What about the kinetic energies of the system at the beginning? At the beginning, the kinetic energy of the system is 0, right? But in the final condition, we have kinetic energy of the bullet here. We have the kinetic energy of the rifle here. So where this energy comes from? Any answer for that? What is the origin of this kinetic energy? At the beginning, it was 0. It comes from the explosion here within the rifle. Let's consider here we have a bullet at the beginning, and here we have a chemical material, gunpowder. Okay. Here there's a gunpowder, let's say, and when this gunpowder explodes, the produced energy is converted to the kinetic energy of the bullet and kinetic energy of the rifle. Okay. So, any question here? Okay, let me continue with example 8.5, collision along a straight line. Two gliders with different masses move toward each other on a frictionless air track. Here we have glider A on the left side, and here we have glider B on the right side. They have certain masses and they have certain velocities. Okay, then they will collide. Okay. After they collide, glider B has a final velocity of plus 2 meters per second. What is the final velocity of glider A? How do the changes in momentum and in velocity compare? So before the collision, the A glider is going along the positive x with 2 meters per second velocity, and glider B is going to the left with minus 2 meters per second because it is going along the negative x direction. And this is the during the collision, and this is the after the collision. After the collision, B is going along the opposite direction to its initial direction. So it is going along the positive x, and A is going to negative x. So we should find a negative value of the velocity for glider A, okay, after the collision. So what about the external forces acting on these gliders? So the surface of the air track is 0 because it is given frictionless air track. And these gliders have some certain weight and there will be normal force, okay? Then the net force acting on the net external force acting on these gliders is 0, okay? Then I can apply conservation of momentum. Then apply conservation of the momentum. The x component of total momentum before the collision is given momentum of the A glider plus momentum of the B glider. Put the numbers here and don't forget to use the negative signs for the velocities along the negative x direction. And then we have the initial momentum of the system. What about the final momentum of the system after the collision? Since the momentum is conserved, this final momentum after the collision will be equal to the momentum before the collision. So then if you know the momentum of the A glider, if you know the momentum of the B glider, then you can calculate this one. Here, we don't know the momentum of the A glider. We don't know the velocity of the A glider after the collision, but we know the velocity and momentum of the B glider after the collision. Put the numbers here. Don't forget to deal with the negative signs. Then finally, we will find the final velocity of A glider after the collision. So it is given with negative 0.4 meter per second. It is negative because A glider after the collision moves along the negative x direction. So the second question, how do the changes in momentum and in velocity compare? So what about the change in the x momenta? This is the change momentum of the A glider. Okay. You can write like this, delta P A, the change in the momentum of the A glider, P2A minus P1A, okay? And you can also write this one for the B, the change in the momentum of the B glider. So what we see here, this is the change in the momentum of the A glider. And here, let me clean this part. This is the change in the momentum of the B glider, delta PB, let's say. Okay, and this is positive 1.2 kilogram times meter per second. And what about the changes in the x velocities? This is the delta VA, change in the velocity of the A glider. And this is the delta VB, the change in the velocity of the B glider. Okay. Any question? Okay, let me finish this part with this example, and then I will go into detail with the collisions. So here, this is the example 8.6, collision in a horizontal plane. This figure shows two battling robots on a frictionless surface. Robot A with mass 20 kg initially moves at 2 meters per second parallel to the x-axis. This is the robot A and this is the robot B. And we are talking about horizontal plane, okay? Both x-axis and y-axis are on the horizontal plane and they are battling, okay, on a frictionless surface. It collides with robot B, which has mass 12 kg and initially at rest. So this robot A has some certain velocity and it collides with robot B, which was initially at rest. After the collision, robot A moves at 1 meter per second in a direction that makes angle alpha 30 degrees with its initial direction. Here, this is the direction of the robot A after the collision and its velocity after the collision. And this is the direction of the robot B. At the beginning, robot B was at rest, but after the collision, robot B is moving in this direction, okay? So, what is the question? What is the final velocity of robot B? Then, first of all, just try to write external forces acting on these objects, robot A and robot B. Along the vertical axis, there is weight of robot B and there is normal force this surface applies on robot B. And for the case of robot A, there is a weight and there is also normal force applied by the surface, but they are equal to each other. So net force along the vertical axis is 0. What about the horizontal axis? Along the horizontal axis, horizontal plane, there is no external forces acting on these two objects. Then you can apply conservation of momentum, okay? So then what about the initial total momentum of the system before the collision? The initial total momentum of the system, momentum of the A robot before the collision plus momentum of the B robot before the collision, and then it is equal to the momentum of the A robot after the collision plus momentum of the B robot after the collision. Then what we have here, B is at rest, okay? Then velocity B is 0, okay? So velocity A1 is given and velocity A2 is given, and the velocity, final velocity of the robot B is asked. So you can take this VB after the collision, then you can write in this expression here. What we have here, we have mass of the A robot, initial velocity of the A robot, and the mass of the B robot and initial velocity of the B robot minus mass of the A robot and the final velocity of the A robot. So here, what about the velocity of the initial velocity of the B robot? The B robot is at rest at the beginning, then its velocity is 0. And here we have this expression, put them here, and you must be very careful here. We are talking about the momentum conservation along the x-axis, okay? First of all, momentum is a vector and it has vector components, and I can write momentum conservation along the x-axis. I can write the momentum conservation along the y-axis. So here in this part, I am writing the momentum conservation along the x-axis. So what about the x velocity of the B? Then here I have calculated x velocity of the B after the collision. So if I apply momentum conservation along the y-axis, then the y velocity of A, y velocity of B, final y velocity of A, final y velocity of B. Initial y velocity of A, it is 0 because initially A object, A robot, has only velocity along the x-axis. It has no velocity along the y-axis. This will be 0. Since the B robot is at rest at the beginning, it is also 0. So then from this expression, you can get the y velocity of B, y component of velocity of the B robot. Then you can find it along the negative y direction, okay? Then here we have x component of B robot's velocity. Here we have y component of the B robot's velocity, and you can calculate the magnitude of the velocity of the B robot, which is given 2.1 meter. And what about its direction? Direction can be calculated by applying this rule. This is the beta angle arctangent minus y velocity over x velocity will give us the beta angle. This is minus 24 degrees. Why it is minus? Because the angle from positive x to the negative y, okay? This is minus 24 degrees, so we have calculated the final velocity of the B robot. Any question here? Then let me continue with the momentum conservation and collisions. Here, within this part, please be careful. We have three types of collisions. One is elastic collision, the other one is inelastic collision, and the last one is completely inelastic collision, okay? Three types of collisions. So if you understand that which one belongs to which collision, which condition, which problem belongs to the which collision, then you can easily solve your question, okay? So please be careful here. Then, first of all, let me give you some information. If the forces between the colliding bodies are much larger than any external forces, as is the case in most collisions, we can ignore the external forces and treat the bodies as an isolated system. What is the meaning of this? So if you have an isolated system and if there is no force acting on the system, then you can apply conservation of momentum, right? But if there are some external forces acting on the system, then what will happen? Okay, this information tells us that if these external forces are much smaller than the forces between the colliding bodies, then you can ignore the external forces. Let me give you this example. Here, for example, we have an A object and here we have B object. At the beginning, we have considered that there is no friction here. There is no friction force here. But let's consider that there is a very small friction force. This statement tells us that if the friction force between the surface of this air track and this gliders is very small compared to the forces these objects apply to each other, then I can ignore the friction force. You can also discuss this situation. Let me draw here. I'm trying to explain this part. Okay, we have two cars and they are moving in opposite directions. This car is moving in this direction and this car is moving in this direction. So here, somewhere here, they collide, okay? They apply forces on each other. So what about the external forces? This car has certain weight and force applied by the surface of the ground, and this car has certain weight and there's a normal force. So the net force along the y-axis is 0. And what about the friction force? So this car is moving in this direction, so there is a friction force due to the friction between the wheels and the road, and here there is also friction force. But if the velocity of these cars are huge and if they apply huge forces on each other, then I can ignore friction forces. I can take friction forces as 0, okay? Actually, there is a friction force as an external force, but I can ignore it since the forces, internal forces, this car applies on the car on the right side and this car on the left side applies on the car on the right side. Internal forces, action-reaction forces are huge compared to the external friction force. Then I can ignore the external forces. Then I can consider that this system is again isolated and I can use conservation of momentum. Then I can consider that momentum is conserved and the total momentum of the system has the same value before and after the collision. Okay, so this is the same statement. If you have an isolated system, then if there is no external forces acting on the system, or if you can ignore the external forces, then the momentum, total momentum is conserved. Okay, then you can apply conservation of momentum in collisions. So now let's discuss the different types of the collisions. One is the elastic collision. In elastic collision, the total kinetic energy of the system is the same after the collision. Okay, so this is the total kinetic energy of the system before the collision. This is the initial kinetic energy of the system, and this is the final kinetic energy of the system. So kinetic energy is conserved in the elastic collisions. Okay, if the forces between two bodies are also conservative, so no mechanical energy is lost or gained in the collision. So kinetic energy before the collision is equal to the total kinetic energy after the collision. In case of inelastic collision, kinetic energy is lost. Okay, so the final kinetic energy of the system is lower than the initial kinetic energy, okay, in inelastic collision. In case of completely inelastic collision, we have two bodies, they are coming with some certain velocities to each other, and after the collision, they are moving together, okay, with some certain velocity. Okay, they stick each other and they move together after the collision. This is completely inelastic collision. Again, in completely inelastic collision, the final kinetic energy of the system is lower than the initial kinetic energy of the system. So I will show examples and then you will better understand. So let me discuss the elastic collisions before the collision now. As I told you, the total kinetic energy of the system is the same after the collision as before in elastic collisions. So then final kinetic energy of the system is equal to total kinetic energy of the system at the beginning. So here we have a glider A on the left side, this one, and on the right side we have glider B, and here we have springs. Okay, then this glider is moving in this direction with some certain velocity. B glider is moving in opposite direction with some certain velocity, and they will collide. Okay, they have some initial kinetic energy at the beginning. Okay, so the total system has some certain total kinetic energy. So what happens during the collision? This has a kinetic energy at the beginning, and this has kinetic energy at the beginning. During the elastic collision, the kinetic energy of this guy and the kinetic energy of this guy are stored here in the spring as the potential energy. Okay, then after the collision, this has certain kinetic energy, this has certain kinetic energy, but the total final kinetic energy of the system is equal to the initial kinetic energy of the system. Okay, so this is the elastic collision, and in case of completely inelastic collisions, what we have here, instead of spring, we have Velcro. You can consider that a tape with some certain glue. Okay, this A glider is coming with some certain velocity. This B glider is coming with some certain velocity. Okay, and then during the collision, the gliders stick together. Okay, due to the glue, let's say here, and then they move together to the certain direction, okay? The system of two gliders has less kinetic energy after the collision than before it, but they stick together and they move together, okay? In case of completely inelastic collisions. In case of inelastic collisions, we have a glider here, A and B at the beginning, and they are moving in opposite directions. So this is the collision, A and B, and after the collision, A is moving in this direction, B is moving in this direction, but at the beginning, the total kinetic energy of the system is this one. At the final condition, after the collision, final kinetic energy is this one. And this final kinetic energy of the system is smaller than the initial kinetic energy in elastic collision. But in inelastic collision, we have the same condition, but the particles, the objects, stick together and they move together. This is the difference between completely inelastic collision and inelastic collision. Any question here? Then let me give you one example for the inelastic collision. The cars are designed so that collisions are inelastic. The structure of the car absorbs as much of the energy of the collision as possible. Then this absorbed energy cannot be recovered since it goes into a permanent deformation of the car, okay? So let's consider that here there is a car and here there is another car. They have some certain velocities, okay? And they collide. And after the collision, this car is here and the other car is here, okay? So at the beginning, they have some certain kinetic energy, total kinetic energy of the system. After the collision, they have this final kinetic energy, but this final kinetic energy is lower than the initial kinetic energy. So what happened to the energy? Energy is used to destroy the cars, okay, during the collisions. So some part of the energy is used to destroy the cars during the collisions, and this absorbed energy cannot be recovered, okay? Any question here? This is an example of inelastic collision. Here I will discuss two conditions for the completely inelastic collisions, and then I will finish with the examples. Okay, so let's look at what happens to momentum and kinetic energy in a completely inelastic collision of two bodies. We have body A and we have body B, okay? And we will look at the momentum and the kinetic energy of the system in case of completely inelastic collision. So in case of inelastic collision, here let me draw. This is the VA, this is the VB, and they collide and stick together, and after the collision they move together, okay? They move together. This is completely inelastic collision. If they move together, this is completely inelastic collision. So what about the final velocity of the A object? What about the final velocity of the B object? They are equal to each other because they are moving together, okay? So if the momentum is conserved, then the initial momentum of this A object, initial momentum of the B object are equal to the final momentum of the system. Final momentum of the system. mass of A object plus mass of B object times velocity of both objects. Or you can write this one, MAV2, MBV2, okay? Since they have same velocity after the collision. This is the completely inelastic collision. So if you take V2 from this expression, you can get this one. Let's consider that this B object is at rest at the beginning and its velocity is 0. Then if you put here 0, then you can get the final velocity of the system in case of completely inelastic collision if B object is initially at rest. Now, let me discuss the kinetic energies. This is the total kinetic energy of the system before the collision. This is the total kinetic energy of the system after the collision. Since B object is at rest at the beginning, if you consider that B object is at rest, then the initial energy of the B object is 0. Then the total kinetic energy of the system before the collision is only given with the kinetic energy of the A object, okay? The final kinetic energy of the system is given both the final kinetic energy of the A object and final kinetic energy of the B object, since they have same velocity because they stick together. Okay, I can write the total kinetic energy after the collision like this. Then here we have V2x squared. Here I have V2x. If I use this V2x here in this equation, then I can get this expression. Then I can get the ratio of final to initial kinetic energy here. This is the final kinetic energy of the total final kinetic energy of the system. This is the total initial kinetic energy of the system. And this is the mass of the A object. This is the total mass of the system. And don't forget that we have considered that B is initially at rest and we have completely inelastic collision. This is the ratio of the total kinetic energies before the collision and after the collision. Look at this equation. What do you see here? This is the final kinetic energy. This is initial kinetic energy. And this is the mass of A. This is the total mass of the system. This is always bigger than this one. Then this K1 is always bigger than K2, or K initial is always bigger than K final. Okay. Here we have considered B object is initially at rest. Even when the initial velocity of B object is not 0, the kinetic energy after a completely inelastic collision is always less than before. So this condition still holds. Any question in this part? Then let me classify the collisions. Okay, we have learned inelastic collision, we have learned completely inelastic collision, we have learned elastic collision. Okay, so what about the difference in between? We have already discussed, but here I would like to summarize them. In an inelastic collision, the total kinetic energy after the collision is less than before the collision. A collision in which the bodies stick together is called a completely inelastic collision. In elastic collision, the total kinetic energy before equals the total kinetic energy after. Final total kinetic energy is equal to initial kinetic energy. And here we have final kinetic energy is lower than the total initial kinetic energy. Here we have final kinetic energy is lower than the total initial kinetic energy. But what is the difference in between that? In a completely inelastic collision, the objects are moving together. And in any collision, this information is very important and can help you a lot when you are solving problems in any collision, inelastic, elastic, completely inelastic, it doesn't matter, in which the external forces can be neglected if there is no external force, or there are external force but they can be neglected, then the total momentum is conserved. So you can apply conservation of momentum to all these types of collisions if the external forces are zero or they can be neglected. Okay, here again we have schematic representation of the elastic collision. Kinetic energy is conserved. This is the before the collision, during the collision, after the collision, and kinetic energy is conserved. In inelastic collision, some kinetic energy is lost, okay, like car accident, okay, car collisions. So in completely inelastic collision, bodies have same final velocity, they stick together and they move together. These are the differences between the collisions. Okay, here I have two examples and then I will finish my lecture. Okay, just two examples. Let me continue with the ballistic pendulum. What is ballistic pendulum? This one. There is a wood here. It is suspended by using ropes, okay, or strings. And here there is a bullet, okay. And this is the condition before the collision. And whenever this bullet enters into this wood, this wood has this type of behavior. This is called as ballistic pendulum, okay? Figure shows a ballistic pendulum, a simple system for measuring the speed of a bullet. A bullet of mass mb makes a completely inelastic collision with a block of wood of mass, which is suspended like a pendulum. After the impact, the block swings up to a maximum height in terms of h, mb, and mw. What is the initial speed v1 of the bullet? Okay, we would like to find the initial speed of the bullet. So this is inelastic collision because what happens? At the beginning, this wood, suspended wood, is at rest, and this bullet has certain velocity on the left side, and during the collision, the bullet enters into the wood, okay, and what happens? The total initial kinetic energy of the system is lower than the final kinetic energy of the system because some part of the energy is lost here due to the friction, okay, due to the friction between the bullet and the wood. So what happened to this lost energy? This energy is converted to the thermal energy and the bullet and wood becomes hot, okay? So now let's apply conservation of momentum along the x direction. So at the beginning, what about the momentum of the bullet? At the beginning, momentum of the bullet is given with mass of the bullet times velocity of the bullet. What about the momentum of the wood? It is zero because it is at rest, okay? Then put it there. The initial momentum of the system, momentum of the bullet, momentum of the wood is zero. Then what about the final momentum of the system? Final momentum of the system is given with this expression because they stick each other and they move together, okay? Then I can write it like this: total mass of the system and velocity of the system. Then I can calculate the velocity, x velocity of the bullet, okay? Here we have two stages. Maybe I should mention these two stages before I execute the problem. So look at this one. During the first stage, the bullet embeds itself in the block and the block swings upward. So just consider for very short moment, okay, bullet enters into the wood. This is the stage 1, and then they move in this direction together, okay? So this is the stage 2. In the first stage, the bullet enters into the wood so quickly that the block does not move appreciably. We consider like this. The supporting strings remain nearly vertical, so negligible external horizontal force acts on the bullet block system, and the horizontal component of the momentum is conserved. Then we have applied this momentum conservation, and we have found the initial velocity of the bullet. But here in the first condition, mechanical energy is not conserved during this stage because a non-conservative force does work. What is non-conservative force? Here we have a friction force between bullet and wood, okay? Then some part of the kinetic energy is lost. We have already discussed this one. In the second stage, the block and bullet move together here. In this condition, they are moving together. The only forces acting on this system are gravity and the strict tensions. Okay, gravity and string tensions. So, as the block swings, the mechanical energy is conserved. They are swinging. So momentum is not conserved during this stage. In the second stage here, during this condition, momentum is not conserved because there is net force, net external force acting on the bullet wood system, but the mechanical energy is conserved, okay? At the beginning, in the first stage, this is very important, you must understand this part. In the first case, just bullet entered into the wood, then here we have tension force on the springs and we have weight like this, okay? And the net force along the Y is 0, okay? Just when the bullet enters into the wood, okay? Then I can apply conservation of momentum here in this case. But in case of this condition, stage 2, these are the tension on the strings and this is the weight, and now we have net force acting on the system along the y-axis. So if the net force, if there is an external net force acting on the system, momentum is not conserved. Okay, I cannot apply conservation of momentum in this case, but I can apply conservation of mechanical energy. So what about the conservation of mechanical energy? It is moving like a pendulum like this. This has certain mass and certain velocity in this direction. This is the height. And here at this position, velocity is 0 and it will go back. So here we have kinetic energy, which is given with m1/2 mv square. And here at this condition, velocity is 0. But since mechanical energy is conserved, here we have potential energy, which is given with mgh, okay? So we have conversion between potential energy and kinetic energy during this swinging movement of the system, okay? We are talking about the second stage. of the system. Okay, here during the second stage, mechanical energy is conserved, but momentum is not conserved because we have external forces. Then I can apply energy conservation. Okay, so the initial kinetic energy of the system at the beginning, and what about the final kinetic energy of the system? Actually, I'm talking about this one. K1 plus U1 is equal to K2 plus U2. Initial kinetic energy of the system is given with this expression. What about the initial potential energy? If I consider that this level is y is equal to 0, then this potential energy is 0. And what about the final kinetic energy? When the block and pallet are staying here, they have no velocity, then their kinetic energies are 0. And then what about the final energies? Final potential energy is given with this expression. So initial kinetic energy is converted to the final potential energy. Then from this expression, I can get this velocity relation, velocity 2, the final velocity of the system, which is given with square root of 2gh. And here we have calculated the initial velocity of the bullet, and it depends on the final velocity of the system. So the final velocity of the system is calculated here. Put it this expression, then you can calculate the initial velocity of the bullet. Any question here? Okay, my last example. Then I finish my lecture. An automobile collision. Here we have a car, a 1,000 kilogram car traveling north at 15 meters per second collides with a 2,000 kilogram truck traveling east at 10 meters per second. Here, let's consider that there are traffic lights, but both car and truck drivers do not consider these traffic lights, and the drivers wearing seat belts are injured during this collision, let's say, but two vehicles move away from the impact points as one. The insurance adjuster asks you to find the velocity of the wreckage just after impact. What is your answer? So velocity of the wreckage. This one, the velocity of both truck and car. What is the velocity? So this is an horizontal plane, okay? So what about the momentum conservation? Let's check whether the momentum is conserved or not here. What about the forces acting on the track? There is a weight and normal force. There is a weight and normal force also for the car, and there is also friction force on the surface of the road. But since this truck and this car will apply huge forces each other compared to the friction force, since these internal forces are huge, then I can ignore friction force. I can ignore friction force as an external force. Then, since there is no external force, or since I have ignored the external forces, I can apply conservation of momentum. So what happens? So this has certain velocity and certain momentum. This has certain velocity and momentum. But after the collision, they stick each other and they move together. Okay, this is inelastic scattering. So I can apply momentum conservation for the inelastic scattering. So what about the momentum of the system before the collision, and what about the momentum of the system after the collision? So this is the momentum along the x-axis before the collision. This is given with the momentum of the car along the x-axis. This is momentum of the track along the x-axis. And momentum of the car is 0 because the car is moving along the y-axis, okay? It has no component along the x-axis, then it is 0 here. So then we have x momentum before the collision. And what about the y momentum before the collision? The momentum of the car along the y-axis, momentum of the track along the y-axis. So what about the momentum of the track along the y-axis? The track is moving along the x direction, so it has no component along the y-axis. So then we have y component of the momentum. So what about the magnitude of the momentum before the collision? I have x component, I have y component, then by using this expression, I can calculate the magnitude of the momentum. And by using this expression, tangent theta is equal to y component over x component, then I can calculate the angle. So I have calculated initial momentum. Since the momentum is conserved, the final momentum of the system after the collision will be equal to the initial momentum of the system. Then, by applying this rule, I can easily solve this question. So, after the collision, the momentum of the system is like this. Total mass of the system, mass of the track, and mass of the car here, okay? Since they stick together, I have total mass here. This is the final velocity of the system. They move together. So if I take velocity here, then it is given with momentum over total mass of the system. I have calculated initial momentum of the system. Then I know the total mass of the system. Then I can calculate the final velocity of the track and car. With this transparency, I finished my lecture. So next lecture on Thursday, we will continue with elastic collisions. We will talk about center of mass, and we will finish with rocket propulsion, which is also very important in technological applications, for defense applications, for space applications. So take care of yourself. Bye-bye.